John will now tell us about the topological string interpretation of Chern-Simons.
So before I started, Diogo asked me to also mention that this has a version that works for open as well. And he said that you need to hear this sentence before the end of the talk, so you have. I've fulfilled my promise. But I'll try to mention something, but I will focus on the closed case, which means that I'll not have Wilson loops. I'll just talk about Chern-Simons invariants alone. And also, I have to realize that as I was rehearsing yesterday, I had to start from page 3 of the notes to have a chance to finish, which I'm going to do. And then the first 2 pages will be condensed into about a minute. So let's see how that goes. Right, so let's just look at some generic open strings, the settings in open strings. By the way, that's going to be a very different talk compared to what you have been hearing this week. So you will see what I mean. So open. Okay. So essentially, what string theory does is that it looks at dynamics of little strings that propagate in space, and then the open strings are those that could end on certain objects, and these are called branes. And then the reason I've drawn several of these parallel is that sometimes you can have so these sort of hypersurfaces are where those open strings can end, and then so sometimes I'll have a whole stack of these sort of coinciding with each other, but I'll just give them let's see, 1, 2, 3, all the way to n. So they are not separated as I have drawn, so they are all together, but just with a different labeling, which means that each, even though the sort of the physical position of the endpoints of an open string is the same, but they can have a label, which means that this ends on the ith sheet or the jth sheet. So that's just an extra labeling that I can get by considering a whole stack of branes. And then one of the key things that I'll do today is that I'll let n go to infinity and see what happens. Okay.
So how should we think about this? The fact that there's more than one copy?
Yeah, so that's how we realize the gauge, let's say SUN. We'll see. I mean, for now it's just an extra labeling. Okay.
But maybe one could say something like, you can choose the boundary condition. You have a labeling, so you can choose either one of them to end on.
Mm-hmm.
And then somehow the magic in all this story is that the short strings stretching between these coincident branes are kind of governed by U and gauge theory.
That's right. Yeah, that's literally my next sentence. So regardless what kind of string theory, usually the expectation is that if you look at whatever that means, low energy approximation, the string theory will be approximated by some kind of gauge theory. So it's not always easy to identify this gauge theory. So let me just write some gauge theory. Let's say with gauge group, in this case SUN. So if you want SON or SP, then you have to put the branes in some fixed locus of some symmetry. But I'll not be using those. I'll focus on the unitary group just for this talk. Okay, so I said that this is only an approximation. So the string theory gets approximated by a gauge theory, and I haven't said what gauge theory is that. But there's one situation in which this approximation is exact, which is the case we are going to look at, which is let's see. So which is if I take the string to be a special type, which is the topological string, on this kind of spaces, T star of M is a 3 manifold. And then then the corresponding gauge theory that approximates it is the Chern-Simons theory, and then this turns out to be an exact approximation. So this is actually, I don't know, exact. My first 2 pages of the notes aimed at explaining why is this exact. But so now I have to do it in a minute, which let me just say that if the strings theory happen to be topological, that means that essentially the only thing that's interesting are in the zero energy sector of the string theory, which means that taking the low energy limit, namely that you throw away the high energy sector, does not cost you anything. So nothing interesting happens there. That's why this approximation is actually exact. So that's Chern-Simons theory on this side. Okay, so that's 2 pages gone. That's good. Right. So there actually is a lot more supporting evidence for this claim, but yeah, unfortunately. So the next thing I want to talk about is, okay, I'm going to take n to infinity, which means that I want to present some general features of gauge theory, what happens when n is big. So general. Okay. So when you take the rank of the gauge group to infinity, that entails certain reorganization of your computation. I'm trying to be vague here. So by computation, what I meant is a Feynman diagram computation. There's a way to reorganize them, out of which the sort of string picture will arise. So maybe you have seen, well, I hope you have seen what's a Feynman diagram. So these are kind of cartoons of interactions. So let's see. Let me just draw something random. So this cartoon just means that, okay, you have some kind of gauge particle, let's say the gluons, that propagates for a while and then splits into 2, and then splits further, and then these combine. You know, that's the. But I'm just saying that this is a lot more than just cartoons. It's got precise meanings in physics. But here, all I want is some generic features, which means that yeah, okay. Okay, so as I said, this is describes the propagation of the gauge particle, so namely the gauge field. So let's so this is a gauge field A. So the gauge field A, that's a one form valued in the Lie algebra. So that's a one form valued in the Lie algebra. Okay, so which means that it's essentially an n by n matrix, and also since n is gonna be big, I'm not going to be I will not be too careful about the distinction between SU and U. So this S will it's not going to be important for us. Okay, so one way to understand, now I want to redraw this diagram with these, okay. So I'll just put the indices, so this is the I and jth, the ith column and jth row entry of the matrix. Now I want to redraw this diagram with these indices explicit, which means that this guy, this wiggly line, will be represented as 2 lines. Okay, just so that I can remember that I have an index I and an index j. And then also just to remember that one is the upper index, the other is the lower index, I just put an arrow. So sort of one arrow means that it's an upper index, the other arrow means that it's lower index. Okay, so now then this diagram, which is kind of like one gauge particle splitting into two, could be redrawn as like this. And then you have a labeling J, I, K, J. Okay, so that's just a scheme of remembering that I have all these indices. So, right. Now, let me just draw some diagrams and show somehow that the Riemann surface picture will arise. Let me draw something like this one. This one in the new representation will be like this. Any questions so far? Yeah.
How do you read that the matrix, the ij, the difference between ij from the diagram? I mean, if you flip it 180 degrees, it becomes ji, but the same. It looks exactly the same.
Yeah, it will turn out that we're only going to get oriented sort of. This is a ribbon diagram, so we're only going to get oriented ones, which means that you can always just choose a consistent one. I mean.
Is this like input and output?
Yeah, yeah.
It's good now.
Yeah. I guess you're asking if you're looking at from here. What?
Like that.
It's not going to be important. It's not going to, yeah. This is, it's not going to be important. Okay, so now the magic here is that, okay, so these index, so I, j, and k, they can take any value between 1 and n. Okay, so which means that so I have 3 indices. They can each take n values. So I'm going to get an n cubed factor to this diagram. Okay, now I'm going to also throw in some coupling, which means that whenever I see a gauge particle split, I'm going to insert a coupling constant here or here. So which means that this guy has got g squared n cubed. Okay. Now let me just for a bit of variation, let me draw a different diagram to show that you get something interesting. Oops. So this is a different diagram. I can also put the orientation on it. Like that. As you can see, that the difference between the two diagrams is that one is planar, the other is not. And let's look at the factors that I can, so what are the g and n factors that I can associate to this diagram? Well, as we have seen that the power of n is essentially the number of components of these sort of closed loops. And in this case, there are only 2, so there's one big one. Then the other one is this guy that goes through the wrong way. So which means that I have only 2 closed loops. That means I got n squared, but I've got 1, 2, 3, 4 splittings, which means I got g to the 4th. Okay. Now,
so what is g?
G is it's you associate coupling to each time when you have a split like this, like each 3 valence vertex you associate a number coupling. That's going to be the electric charge, but there's no need to go there. Okay. So the old idea by 't Hooft is that, okay, I'm going to send n to infinity, but keep this combination fixed. So g squared n is held fixed, and this lambda is called 't Hooft coupling. And unfortunately, this lambda is the log of Thomas lambda. So anyway, so which means that I can write this as lambda n squared since lambda is being held at finite value when n goes big, so you see that this guy will dominate over that guy, which means that planar ones will dominate over non-planar ones. Okay. And then the general formula, if you draw an arbitrary ribbon graph, and then the general formula is okay, so the power of n will be given by 2 minus 2g. So g is the genus. So this guy has genus 0 because it can be drawn in a planar fashion on a sphere. This guy has genus 1 because it can be drawn as a planar diagram on the torus. So genus 1. So the power of n is given by that. And then the power of lambda is given by the same thing, but with the number of holes, you add the number of holes.
Or G is the genus and not the coupling constant.
Yeah, that's unfortunate. That's right. Yes. Right. Put a bar here, a tilde or something. I'm really sorry. But anyway, that's the last time you're going to see the coupling, because after that I'll be working with lambda alone. So sorry. So Thomas pointed out, not Thomas. Marco pointed out that this G is the genus, not the coupling. So
You can call it chi. No.
yeah, I can call it chi. Yeah.
This
is minus chi.
Or you could say G sub s for string.
Yeah, exactly.
Yeah, 1 over n, that's the string coupling. But that doesn't solve the G problem. The genus, never mind.
What is the formula?
Sorry?
So what is the formula?
So if you draw an arbitrary diagram, ribbon graph, and then the power of n and the power of lambda will be given by this formula. Okay.
Okay.
So now this is where the picture.
Lambda is always G square n.
Yes. Lambda is G squared n. Yeah. So this is the place where the Riemann surface showed up, because I've already alluded to the fact that these are ribbon graphs, and then ribbon graphs are just used to. It's one way of representing open Riemann surfaces. So for example, let me just draw it like here. Let's say Riemann surfaces plus, so this guy will correspond to a sphere plus 3 punctures. So you have 3 holes. So a sphere with 3 punctures. And then let's say a torus, can't find a good place to. So a torus, say with a puncture, you can just write it as like that. Okay, so they're always written in terms of some kind of ribbon graphs. Okay, so that's how we got the first inkling. It's actually about 40 years ago that we got the first inkling that gauge theory, when n is big, should have something to do with string theory. But at that time, too, didn't have enough technology to go on, so that's kind of the end of the story. So let me just tell you what the goal of this talk will be in the end. Oh, why did I do that? What I would do toward the end, what I hope to achieve is that there's another arrow. Sorry, I should have not erased it. This is called a geometric transition.
Sorry, John.
Yep.
Maybe I missed it. Was there some explanation for why this particular combination of powers, lambda?
It's just that.
It's so elegant.
Because well, you know that the power of G will be given by the number of vertices, and then the power of n will be given by the number of boundary components, and then you play with the Euler character. You get that. Okay, so there's an arrow to the right, which is called a geometric transition, which will lead us to closed topological strings. Sorry. erase that as well. On the resolved manifold, I'll explain what are these things. And then what's so great, okay, let me just recap. I have a central picture which is open topological string on this space. On one hand, it is exactly Chen-Simons theory on S3, and on the right, you have a transition to a closed string theory on a different geometry related to the other one. And then the great thing is that both this side and the other side are computable. So what I will do is that I'll just take the exact result here, do a massive change of variable, show that it gives you something with the structure of, matching the result here. So that's my goal. So, any questions? So let me just say very quickly what's this geometric transition. I kept erasing the stuff I need. Okay, so I'm starting from T star of S3, which I'll write. I'll present it as a subset of C4 cut out by the following equation. So I'll have complex coordinates z1, 2, 3, 4, and then I'll write each guy as the real and imaginary part, and then I'll impose the following condition. So I'll say that the sum of squares is equal to a positive number mu, and then if you write down the real and imaginary parts, you get two equations. This leads to So the real part of this equation says that the norm of x squared and norm of y squared is equal to mu, and then the second one says that they are perpendicular. And then notice that from the first equation, if I say that mu is bigger than 0, then x can never be 0. Which means that I might as well normalize it to have length 1. Okay. Questions so far? I think maybe most of you have seen some version of this story at some point. Okay. So the geometry will be such that this is now a unit vector in R4, which means that it's a point on S3, and then since y is perpendicular to x, that's the cotangent direction. So this gives me the geometry of T star S3, and then I'll just write it. I'll draw a cartoon to represent the geometry, and also represent the geometric transition. So I'll draw a rectangle.
I'm sorry.
Yep.
There is one more condition other than y being perpendicular to x. So there is this difference of squares of north being equal to mu. So
right.
Yeah, this one. So it's not the whole cotangent bundle. It's something small.
It's the whole, because y can be as large as you want. And y parameterize the fiber. It can be as long, as big as you want.
But how can it be something fixed then?
So long as I make x big, right?
When you map to the sphere, you map x to the unit version of x, and you readjust the y.
Ah, okay.
This is the mapping to the.
Okay,
this
okay,
node.
okay, okay.
You don't put the norm x as 1 as a condition. It's just when you map, that's
Okay.
how you map to the
Okay,
sphere.
okay, okay.
Yeah, I'm just saying that the map goes that this guy is a point.
Yeah,
in
the
S3.
third line is not one of the conditions, not one of the equations. It's a
Yeah.
map.
It's something you can do.
Yeah.
Okay. So I'm going to draw a rectangle to represent. Sorry. So one side I'll just call it S3. I'll use this to represent S3, and then this side to represent S2. So what is this S2? That's the, if you want, that's the unit cotangent bundle of T star of S3, which is well, it's going to be an S2. So because because in this geometry the fiber can go to 0 size. I mean you are able to access to the 0 section, which means that the size of S2, the S2 can be filled in. So you got this sort of. Oops. So this is like the 0 section of T star S3. Okay. Any questions? So when you go out to far away in the fiber direction, you're going down. So the fiber gets bigger and bigger. All right. Oh. And then so the geometric transition has this cartoon, which means that I'm gonna shrink the 0 section to 0 size first. Whoops.
So that whole S3 collapses through.
Right. So the size of S3 essentially is controlled by mu. The mu controls the size of S3. So I send mu to 0, then that means that the size goes to 0. So I'll do this first, and then after that I'll sort of blow up the S2 part, which means is this picture understandable? So I go like this, and then I go like that. So now this becomes an S2. So this is still an S3, except so the difference being that now before the S2 was filled in because I'm able to shrink S2 to nothing, but here S3 can be filled in because now I can shrink S3 to nothing, but the size of S2 is finite. Again, the size of S2 will be given by mu. Right. So in formula, what does this cartoon mean? So this just means the following. So as I said, I'm going to first send mu to 0. So I can rewrite this equation as then I'm gonna just call these guys some new names by some new names. So I'll call this combination U, V, U tilde, and V tilde. Okay, so the original equation in the limit when mu is equal to 0 goes into UV plus U tilde V tilde equal 0. Okay, so this is the singular conifold because actually at the place where UV U tilde V tilde is equal to 0, there's a Z2 singular. Okay, great. Okay, so there's a Z2 singularity at the origin where all the UV and U tilde V tilde are equal to 0, So I'm going to resolve it, and this corresponds to this step. Oops. So, well, in one word, what is resolution? Resolution means that you just remember in which direction did you approach the singular point, okay? And then, which means that okay. So I've got one more z, but this z has got nothing to do with the 4 z's here. It's another z. So as I said, resolution, doing a resolution means that you just remember in the direction in which you approach the singular point, and then the direction as you approach u, v, u tilde, v tilde equal to 0 is parameterized by this number z here.
So this is the direction from which you approach.
Yeah.
Mathematicians call this a flow.
Yeah.
Tilde
Sorry?
in the second.
Right, and then so the z is just the stereographic coordinate of S2. Okay, so z can go from 0 to infinity, and then so it parameterizes an S2. So that's the coordinate here. Okay, so. Right. So let me just say very quickly what happens to the branes across this transition. So before, let's recall that on this side you have T star S3, and I have n branes on the 0 section of S3, but the 0 section is here, so I've got lots of branes here. So as I shrink the 0 section to nothing, these branes disappear. Okay, so on this side, there's no brane left. And then, so by request of Dioga, I should say that if I do include the Wilson loops, then there'll be some other branes on this side which will survive this geometric transition. Okay, but I will not have time for that. And also, I believe Tobias once told me about there are some erroneous notions of how to track the fate of these branes across the geometric transition in the literature. So not everything you read is correct.
Well, things are correct just to varying degrees. I mean, it depends on your definition of correct.
Yeah, this sounds very sinister, though.
There are a lot of, I mean, there were some kind of papers producing heavily abstracted Lagrangians that are not good for this stuff.
Yeah, I mean, so they're fine, but
they're fine,
they
but
don't
they
achieve
won't,
what we want.
they won't.
Yeah. I don't want to drag us into politics, but variation of the definition of correctness is what gets us into today's mass, I think. So, but anyway. Where was I before this Orwellian remark?
Blow up. Transition.
You just blow up.
Yeah, okay. I blew up the S2. So, and then the branes disappear. So what happens now is that on this side, there was one ingredient I didn't talk about, which is some kind of vanishing theorem, which says on this side there's no holomorphic disks. And on this side, now I have no branes, but I have a S2, which is a rational curve. So I have some holomorphic curves in there, and then the counting should be really easy because, in fact, the counting of curves will be just multiple covers of the S2. Okay, so in the last maybe 10 minutes, I think, I'll do what I promised in the beginning, namely, I'll write down the answer for the Chern-Simons theory on S3. I write down the curve count on this side, and I'll show that they coincide. Any questions?
So the point of this geometric transition is to pass from open strings to closed strings?
Yeah. Yeah, I don't think it's terribly clear why well, there are some physics arguments about this. Again, this is, I think, too hand-waving to be presented here. Okay.
Is this part of the general story, or like is it very case specific?
For T, for T star M, this is generic. So, okay.
For T star M, where M is not necessarily 3, you are saying.
No, for three for
Three
general.
man.
But we don't, I mean, we don't know of health partial is resolved conifold for other things than geometric portions of S3. Right?
That's right.
Yeah.
That's right.
So for other things we don't really
Yeah.
know, I think.
But the great thing is that I think the physics argument will survive all that.
Well,
Well, the physics argument has nowhere to lead, right?
They always have a sigma model interpretation. So that's kind of, but I don't think it's wise to go there now. Right. Okay, so let me just say, first of all, on the consignment side, the exact result can be computed. Okay, just to save some time. Okay, so on the consignment side, the exact result is known. I think I might just give a response to your question. You objected to that the perturbation expansion of consignment theory is an asymptotic series for large K. But to reach this, there's some kind of resummation going on. So you're able to resum an asymptotic series into something well-defined. Okay, but this is far from being clear. Right.
So what is the factor just before pi? Is it delta? Or is
2.
It 2. No, in the numerator before pi.
S.
S pi. Okay.
Right, and then on the closed string side, let me just say what we expect. Okay, so oops. Okay, so we have this genus expansion. So as Lenny was remarked earlier, that 1 over n is essentially, did I get the wrong sign? Yeah, that's correct. 1 over n is the string coupling, which means that higher genus is suppressed when n is big. Okay, and then this is the contribution for genus G. And also I will make a simplifying assumption that H2 is one-dimensional. I'm not going to write it. So the structure we expect, which means F0, 1, 2, etc., will be of this type. Okay, sorry about that. I just defined a new variable. T, I call it I lambda. Lambda is here. So just because I don't want to write I all the time. But so this is the structure for genus 0. So let me just say that all of these prefactors, these summons, they all have geometric interpretations. But let's just leave that.
Sorry, what's X? Sorry, what is that?
Chi.
Chi.
That's the Euler number of the target space. So that's going to be 2 in this case.
What's the term that follows it?
Zeta 3. Zeta 3. So as I was saying, there are geometric interpretations for all of those. But so what I want to draw your attention to is this final term, which comes from basically this dm. That's the number of rational curves of genus of genus m, and then n is the summation over n. That's the sum over multiple covers. Okay, but so for our story, that's much easier because the only curve in our geometry is of genus 0. That's the S2 that we blew up. Okay, so dm would just be 1 all the time. So this is what we expect for f0. And then let me skip over f1. Just write fg for g bigger than 1. Okay, so there are a lot of stuff here. Let me just say what are these things. So the second half is kind of easier to recognize. Again, this is some summation over multiple covers of curves, and then this part, what's chi sub g? Chi sub g, that's the Euler character of the Ling-Mumford space of genus G Riemann surfaces. So if you want, this chi sub g has got an expression which is worked out by I believe it's Faber and Pandaripandi. So it's got this concrete expression, and then dg is the Bernoulli number. Okay, so let's just pause and think about what is it that we are expecting to see. We're expecting to see that this guy, when I take a logarithm, should have an expansion in terms of f0, 1, 2, etc. that somehow will incorporate all these structures. So I think I'll be pretty convinced if things turn out to work. Okay, I think it's sort of like a miracle, I would say. Right, I have 5 minutes. So I think what I would do is that I would just give you an inkling of how things work out. Especially, I want to be able to recover. Where was that? I want to be able to recover this sum, and I want to be able to recover the Bernoulli numbers. So I think the rest is fairly easy. But I have to say that when I did this myself, I tried to get the other factors correct, but I got almost all of them wrong.
So let me see, you're scheduled until 40, right? So even if you take a little bit more than 5 minutes, it's okay.
Yeah, but
I'm not telling you.
It's. I think it's slightly unethical to infringe upon the empty stomach of the audience.
We just had a coffee break.
Yep. Okay. Anyway, so right. Okay, so I'm going to take a logarithm of z, and then I'll reorganize the summation. Reorganize this function into something that. I'll reorganize log of z according to the power of n, because that's the genus expansion. Hopefully, I'll recover all these structures. But to compute this efficiently, you probably need to use a few formulas. Any questions? Okay, so you will need to use the product formula for the sine function, or because you are taking a log, so it's nice to write stuff as in terms of something multiplicative instead of additive. So this is something you need to use. Another formula you need to use is the infinite. So these are formula you will need to use later. So hopefully at least it's clear that what am I getting at. Maybe you will not follow all the steps. Is it clear that what is it that I'm aiming at? Okay. Right, okay, so let me just focus on the things that will be important. Which means that I'm only going to focus on this last sign factors. I'm going to take a log, and I'm going to use this infinite product formula. And I think you can recognize that in this infinite product formula, I have a summation, a product from 1 to infinity. That tells you it's the summation from 1 to infinity. And then this product from s equal to 1 to n minus 1, I'm having a sum from 1 to n minus 1. Okay, so now I need to do the sum over S. So I'll write it in terms of oops.
Did you do something sneaky with the K there?
With the K, I replaced them with lambda, I believe. Sorry, yeah, one of this is lambda. Sorry, yeah. Okay, so what I did is that I rewrite the log of 1 minus something as a power series, which would allow me to sum over S. So let's just look at, so why is it that I'm going through so much detail? I want to show where the Bernoulli numbers come from. Okay, so let's just look at, I'm going to sum this S, which is from 1 to n minus 1. So I'm going to do this one. But the power, oops. But the power of S, let's say you have S squared and L and maybe 1 or nothing. But let's remember that the sum of, let's say, S to the some power from 1 to n is exactly given by the Bernoulli number. I mean, it involves an expression that has got Bernoulli number in it. Okay, so yeah, I think I will not write that down because it's no one is going to spot if I was making up stuff. Yeah, so. So yes, sorry about that. But this can be found in the work of Gobakuma and Wafa. They had all the details there. So now I think I've convinced you where these Bernoulli numbers come from. And then finally this sum of 1 over cube e to the minus this thing. Where does that come from? my notes. Yes, I just wrote something that I said I wasn't going to write. I'm sorry about that. Yeah. So the sum over S, if I do it, it's this expression. I'm sure you have seen this formula somewhere before, but as I said, this is where the Bernoulli number comes forth. And then, so what I will do next is that I will just collect the, remember that the F0 is multiplied by n squared because that's the genus 0 contribution. So I just collect everything that's got n squared in it, and then which it turns out that only the first term will appear, and then you do the sum, which involves some tricks, and in the end you get exactly that. But I'm afraid I'm not going to be able to show that here. But I hope you're convinced to some degree. Okay, yeah, thanks a lot.
Any questions? I have a question. So, is there anything you can explain about what the meaning is of this, I don't know how to say his name, prescription that you take this G squared and to be finite?
Right, so
Can you take a look?
well, I think you have seen, so here I've sneakily redefined T equal to I lambda. Lambda is the n divided by k plus n. And T turns out to be, as you see, it appears in the sort of Novikov coefficient term here. So that's actually, T is the size of the blow-up CP2. So you can say that lambda is the size of CP2. Oh, sorry, CP1.
We're making that smaller.
No, this will be held finite.
Oh, that,
So it's n that's going big.
So is this Z, is that expressed in some open grown width invariance in satisfier 3 or is it?
You mean the Shenzamen's part?
Yes.
So far, without incorporating the Wilson loops, this will be just closed strings. But if you have Wilson loops, then you have also open Gromov-Witten invariance, and also the punctures will be labeled by a symmetric product of fundamental representations.
But I was saying this, is there a homomorphic way to obtain Z? Not that way you describe, but
You mean this one?
Like without transitioning?
Without transitioning, I'm afraid not, because it's just because without transitioning, it amounts to counting some kind of degenerate curves, and it's just not clear how to even define the measure.
I mean, conjecture. So is it related to something? Maybe.
Yeah.
Maybe it is maybe.
Open or written on n copies of.
So that's what people expect that to be done.
Well, that's the picture, but it's typically defined, and it's not going to be counting ordinary homomorphic curves.
Right.
So it's not just open, there's some sort of twisted version of it.
No, just open.
But
There
it's
is
not
a-
tricky to define.
Yeah, that's what I'm saying.
No, but why is it tricky to define? I thought we had open.
No, the vanishing theorem says that there's no such thing. There's only degenerate ones, and it's not clear how to define the measure. Any other questions?